So, hello, this is the assembly group. And if you're in the wrong room, just feel free to stay here. And so today we're talking about Intro to Reverse Engineering. So let's see, where's my mouse? Okay, so here's our links. We're on Slack with the hashtag tag. That will be our Slack channel. And then there's a Facebook group, Facebook page. Feel free to look at that. And then I think we have a website. And then that's our email. So if you like to take a picture of that, go ahead. Yeah.
I noticed that you have a channel on the CSG Discord. Are you going to be posting information on this?
Yeah, we will.
Okay.
Yeah. Yeah, and then I think that was just added today.
Yeah.
Yeah. So that's our links. So today I'll start by beginning by explaining what is reverse engineering. So there's a Wikipedia definition. It's very long and it's very lengthy, and we really don't care about the definition. So it's basically like the idea is to deconstruct some design that's already been built. And then what does that mean? So in terms of assembly, it's basically understanding the underlying structures and design that we have of a program. And in simple terms, it's just reading assembly code. So first of all, I'm going to go through some tips of how you might want to go about reverse engineering. So first of all, with any binary, it's going to be, assembly is very bloated. So what you want to do is start looking for overarching patterns rather than the small details. And then, as I said, assembly is verbose, which means that there's a lot of stuff going on in assembly that some of it, frankly, you don't really care. So it's essential to understand the bigger picture rather than the small, minute details. And then another tip for like if you're starting out with reversing, a good tool to just play around is you just first write some C code that looks very simple, and then try to see what the assembly code is generated, what it looks like. And oh yeah, and if there is anyone that has any question, that's our link right there. Feel free to ask at any time. So let's start with the simple example. So last week we did a little bit of assembly, and so let's see, what does this simple code snippet do? So now we have a simple code snippet. There's a simple loop that you see there. And then we first set RAX to 1 and RBX to 0. Feel free to, I will give you a few minutes to see if you can figure out what this is. So what does it calculate? Does anyone want to give a guess? Okay, yeah, that's correct. That's correct. So here we have a label labeled LBL, and then each time we do a loop, we increment RAX by 1, and then each time we add what's in RAX into, ooh, what's going on? Okay. We add RAX into this register RBX. And then we do that, we compare it, each time we compare RAX with 10, and if it's less than or equal to 10, it will continue to loop. Once it goes above 10, it will actually break out of the loop. So let's see, next slide. So a very important thing that when we work into assembly is how do we do function calling. So in NASMX, if you remember from last week, we actually heavily use invoke statements to call different functions. So then it kind of looks like we're calling a function using the commas. But when we go down into, so kind of like that. That's an example. So here we have a printf. We invoke printf, and then we pass in message as our first parameter, and then a value EAX into our second parameter. The problem is, when we go down into assembly, there actually is no notion of arguments. So there's no assembly instruction that just like invoke. So how do we call functions? How do we pass parameters? So now we go into something called calling conventions. So this is pretty OS dependent and is also like architecture dependent. So if you're working on a 64-bit computer, it's different from if you're working on a 32-bit computer. Same as if you're working on Windows versus Linux versus Mac OS. And it's also even more different if we work on like ARM. So the idea is we have this thing called calling convention, which defines a set of rules for passing, how do we pass arguments. So Linux 32-bit uses the stack. And we'll get to what the stack is in a second. And then Linux 64-bit uses registers. It will first use registers, but then if there's too many arguments, it'll actually overflow into the stack. So we go on to 32-bit calling convention. So we have arguments. So here we have a simple invoke statement, and that's the corresponding code in assembly. So here, this is what we would probably write in NASM X. This is what the code actually looks like. So we really don't care about this one, this instruction, and this instruction. These are used for alignment, but that's not really important. What we see here is we have a push right here. That's our EAX, which is this EAX. And then we have a push of the message. So these push instructions actually push onto something we call the stack. And then what printf would do is they will actually read these arguments off of the stack. Okay, and next. So in 64-bit, we have registers. And then it looks like this. It's a little bit more simpler. So again, we have the same call, invoke printf message EAX. So first of all, we notice that we have a move EAX into ESI. And then I think this one should be RDI, not EDI. Let me scratch that out. But this should be RDI. So, and then RDI is actually the first argument, and then RSI or ESI is our second argument, and then we have RDX is our third, and then RCX, and then so on. And if we have in Linux 64-bit, if we have more than 6 arguments, we go onto the stack. So that's calling convention. So calling examples. So here is an example. So we have this call. Feel free to write down the assembly instructions, what you would think would be in Linux 32-bit. So I think on your sheet there's some blank page. There's a blank page that you can write this down. There's one page. So give you a few seconds. So here's one thing you want to notice, that there's a B plus C. So we're not passing in just a single value. You might have to do some assembly instructions for that. Is anyone still working on this? If you're working on this, please raise your hand. Okay, looks like I think everyone's done with it. So I think I'll reveal the answer. So here is what you might want to do. So first of all, remember, I think on the previous slide it said we push arguments in the right to left order. So we start with the 4 first, and then B plus C, and then A, and then 3. So I think I did make that very clear. That's the case for 32-bit. So first of all, we start with the push 4. So we push the value 4, and then we move the value of B into EAX, and then we add C to EAX, and then we push EAX. So that'll be our third argument. Our second argument is A. So we just push A, the value of A, and then we push 3. And then we make a call statement, which is the last one. So something like that. And then, so there's also one for like 64-bit. And then if anyone wants to try it out, I will wait a bit. Okay. Does anyone is still trying to work on this? Okay. I guess if no one else is working on this, I'll just go through this answer. So basically, here we note that we do put EDI as we start with the 4th argument, which is ECX 4, and then we do the same thing for the 3rd argument. We put into RBX, and then we do RSI and then EDI. So think these PowerPoints are also online. So if you are not really confident with this, you can also look online. We actually post we have the same PowerPoints online, and I think by default we actually cover up that box, the answers, so that way you can actually do it without actually looking at the being able to look at the answers. So let's go on to the next slide. So we'll move on to call stacks. So first of all, we want to ask, what is the stack data structure? So I think you saw that there was a push operation, and there's also a pop operation. But does anyone know what a stack is?
Data structure that has the rule of last in, first out.
Yeah.
So
Okay.
that thing's on, and then they come off in the reverse order.
Okay. So basically, stack is, that's what he said, you have something last in, first out. So the idea is you have 2 operations. You have a push operation that adds more elements to the stack, and then you have a pop operation. So how is the stack implemented in assembly? It has to be really lightweight. So the idea is we imagine the stack as like a range of memory. So in x86 assembly, we imagine that call stacks are the idea of a call stack is just a chunk of memory that has a high address in nature, and it will actually grow downwards from high addresses down to low addresses. So, and then you have the push and pop operators. And then here's the diagram. So on the bottom, you have your program data. That is where your .text data goes. And then you have the stack on the top. So you start with the highest address values, and then the stack will actually grow downwards. So also, the other thing is we actually have something called a stack pointer. A stack pointer tells us where we are in our stack. Since the call stack is just like a big chunk of memory, the stack pointer actually just points to a spot in that chunk of memory, and that's our pointer. So then the interesting thing with call stacks is it actually grows down. So a push operation actually decrements the stack pointer, and a pop increments the stack pointer. And that's really important to remember when you're working with assembly. Okay. So let's actually look at some code. I think that's it. So now we're going to do actually a demo of reversing. So here some reverse engineering tools. The most basic tool you can use is object dump, obj dump, and then you can use the command obj dump -d to dump assembly. And then you also can use GDB to debug a program. And it will actually, and you can also disassemble using GDB. But then there are other tools, reversing tools, and kind of my personal favorite is IDA, which is spelled IDA. That's personally my favorite reversing tool. But there are other reversing tools called Binary Ninja, Radar, and there's Online Disassembler, and that's online. So, yeah. So let's move to our next, see where we have it. Okay, there. Okay, so here I have a little C program that I wrote. And I have the disassembly right here. And let me make sure this one is Intel. Okay, it looks Intel enough. So, so here we start with the, we look at some code. We have the main function. It keeps track of a score variable. And then we also have an incrementer I, index. And actually, let's see if I can everyone see it? Or let me enlarge it. I think, okay, there you go. Is that good for everyone? And I'll enlarge that later. Okay. So here we have the main function. We have a for loop that iterates 10 times. And then we ask 10 questions. And then we quiz a person with 2 numbers. And this number function actually generates a random number between 1 and 20, I think. Or 0 and 19, something like that. And then we call this function called quiz person, which is up here. We ask what is this number plus this number, which are the arguments. And then if the user gets it correct, we say correct, and user gets a point. Otherwise, we print wrong, and user gets no points. So, pretty quick demo of this. So, So if I run, I'm currently in here, so I have to go to programs, math quiz. Oh. Caps lock. Okay, so now we run the program. The program asks what is 9 plus 6 plus 3 is 9. And then this one we ask, what is 15 plus 17? Let's just get it wrong. 45. And that's obviously not the right answer. And this one, 15 plus 13 is 28. And then let's just put in random numbers here. So after we get 10 questions, you say that we earned 0 out of 10 points, because obviously my program messed up. Oh, that's why. Because I didn't do a plus equals. That might be a problem. Okay. No problem. We just run it again. So 32, and then we just do some numbers. Okay, it says you have 2 points because I got 2 questions correct. And then let me update this because now it's not the right one. Okay. So Let me close this out. That's not important. So now we actually want to look into assembly because we're the assembly group. So here, we start with the quiz person. Let's start with the quiz person. So here we have a lot of code, but a lot of this is kind of junky code. So you want to actually take a step back and look at what are some patterns that we see here. So a good way to do it is look at the C code and look at what the assembly says. So here, this is the function quiz person. So first statement we have is we have a printf statement. So here, I think we have the printf right here. Everyone see that? So we have two arguments that we pass in, an EDI, and I think this is 64-bit. So you want to be wary about, you probably will be able to find out if this is 64-bit or 32-bit just from the function calls. But this one we have 64-bit. So we pass the first argument, which is some number, nonsensical number. But that actually is just a pointer because we pass in the string right here. So then we pass in, remember we also pass in two other arguments. One argument is right here in ESI, and then we have another argument that is passed in EDX. So why are we seeing this thing right here? These things. Does anyone want to explain what this actually means? Okay, so if we remember, these are actually variables, local variables. So these are variables that can only be accessed within our function. So that means outside the function, we can't access these variables. Right? And I think last week we also kind of, we were playing with assembly, and then we were storing all our variables inside registers. Remember that? So those of you who are here. And then we hinted that sometimes you can't use variables, or you can't use registers to store all your variables. First of all, there aren't a lot of registers. So if you want a lot of variables, you don't have anywhere to put them. And second of all, sometimes other functions actually modify these same registers. So a way to counter this is we actually have the idea of the call stack again. And we actually store all our variables, local variables, into this call stack as well. So if you see here, RBP is actually another pointer. It is actually known as the base pointer, and it stores, it gives us a pointer to where all our local variables are stored. So right before. So we can see that there is an offset. So RBP minus 0x14, RBP minus 0x18. And notice that these same values are repeated throughout the code. And a way to, if I were looking at this assembly code and I only had object dump, what I would do is actually put a box around it and then maybe annotate what I think this variable means. So that way you actually have an idea, you can keep track of the variable names. So in this case, if you remember our function call, the first argument is actually stored in the DI register. So when we call quiz person, we actually pass in two arguments. We have num1 and num2. So what does this assembly do first? It actually stores the two arguments that we have here in our registers and stores them into local variables right here and right here. So right now I actually don't have anything to annotate that. But for example, if you have better reverse engineering tools, you can actually annotate those offsets. But anyway, the idea is we have this second argument, which is num2, put over here into dx, which is passed as the third argument here. So a lot of it, right now what we're doing is we're trying to kind of piece together pieces of what this is. Therefore, this is what something else. So right now we have a printf. So this is the entire printf statement. And then right after that, we have a scanf. So this thing right here. So what we notice here is we pass in, with the scanf, with the seat, we actually pass in two arguments. A %d, which is a string, and then we pass in a reference to a variable. So not the variable itself, but a reference. So let's see what assembly does. So right here, we actually see something interesting. Again, we have the first argument, which is di, and that is a string. And then the second register, the si, is actually stored. We actually set it from the value of rax. And where's rax set? It is actually set in the previous statement using a li statement. So li is a fancy word for just getting the address of a memory. So in this case, we're just getting the memory of where this local variable RBP minus C is, hex C. So that is actually the same thing as our this local variable right here. So right now it might seem a little bit over your head, but the idea is what I'm doing right now is actually just corresponding the C code to what the assembly looks like. And then that way you could be able to start get some correlations. So now we actually, after we do a scanf, okay, so now we call the scanf. So this is our scanf. Now we have some more. Now we get the value of two of our local variables, hex minus 14, hex minus 18, which is the two arguments up here. And then we add them together, which is what we have over here. And then we get the value of this thing, our local variable hex C. And that is actually stored in our scanf. And when we did our scanf, that is our res variable. So we compare if these are correct. If these two values, this is edx, which is the result of our add, and this is eax, which is what the user inputted. If those two things are equal, we get to this statement. We don't make a jump. So this is a jump if not equal. So then the idea is we keep moving on, and we do this thing. And then we move eax into 1, or 1 into eax. But then if we don't do it, we see that we have an address here. We jump to something 32. So we jump over here. And we put 0 into eax. So now you might ask, why are we putting 1 or 0 into eax? What's eax? Because we're not actually using eax here. So you see that you don't see eax anywhere over here. But if we look at our C code, we see that we have a return 1 and we have a return 0. And if the answer is correct, we return 1. Otherwise, we return 0. So the idea here is the eax register is our return register. So if we wanted to return a value, we return it via eax or rax. And then so now we go down to main. There's more code, but I think it's a little bit more. It's just more code. So I will move on to the next part. So do we have the handout? I need a handout to look at. Okay. Thank you. So right here, I have some instructions for SSHing. So the idea is I actually have a server, and I have written a vulnerable program that you can play around with. And then instructions are in your packet or in your handout. But you don't have to do that right now because what I need you to do is actually already printed on your page. So skip. Feel free to skip. Right now we're skipping steps 1, 2, 3, and 4. I think. Okay. Yeah, I think we're skipping steps 1 through 4 right now. But feel free to get back those on your own time. Okay, so we're actually going to move on to step 5. So right now I actually printed on your last page, I printed out the assembly dump of 2 functions. So there is a vuln function, VULN, and there's a main function. And the main function goes on both pages. So for lack of time, I'm just going to briefly go. So right now I actually have a screenshot, and this is some image editing. So why am I pulling up an image editor? The idea is right here, I want to be able to mark up this text. So like looking at assembly like this is often really difficult to figure out what is going on. So what I like to do is I like to draw arrows to point to where these go. So for example, first of all, do we see any jump instructions? So we see one. Let's see if I get a color. So okay, cool. So I see one here, and I see another one right here. So they start with the J. So we have 2 jump instructions. So here we have an address, 2 addresses associated with each jump instruction. So what I wanted you to do is draw an arrow to where this jump instruction will jump to. So for this jump instruction, we see that this corresponds to address 485CB. So I think is right here. So just draw an arrow to here. And then the same thing, what we want to do is do the same thing for the other one. I think it goes right up here. Okay. So, and then, so, might be a little bit unclear, but right here we actually have some sort of loop, because we see that there is a jump statement that actually jumps back, and it's a conditional statement. So this is usually the hallmark of some sort of loop. So now, yeah. So now we want to look at calls next. What does this function call? Can any one of you raise your hand, see if you can find one of these calls? On. Okay, printf, and what else? Get. Oh yeah, PLT. Yeah. So we have 2 function calls. So for this one, we want to be able to annotate those as function calls. So I think a good way to do it is actually boxing it. So let me change to a different color, and then let's just box it. So this, we have this instruction here. Let's see. Okay, here. So that's one call, and then we have another call. So now you notice that if you look carefully, when I box these things, do you notice that when I boxed it, I actually added the add statement afterwards? Does anyone want to give a guess as to why I have also boxed the add statement as well? as part of the call?
The cleanup.
Okay, I heard something. Can you say it louder?
It's the cleanup for the stack frame.
Okay, so it's a cleanup. Does anyone else want to give a shot of explaining?
It undoes some offset introduced.
Okay, yeah, cool. So, if everyone remember, we actually did some pushes before, and then we modified the stack pointer. So we want to be able to undo those changes we did to the stack pointer. So that's why we have the add afterwards. So this is a hallmark of something that we would do in 32-bit Linux. So the previous one we did 64-bit, this one is 32-bit. Okay. So next thing, so now we want to look at some variables. So notice how we actually haven't looked at every single instruction yet. So I think with starting off with assembly, there's a lot of instructions that you can just ignore, but you just want to get the patterns that are embedded inside the assembly code. So now I think we want to be able to we want to be able to figure out what variables are being used. So I see a 0C. Let me enlarge it, see if, okay. So I see a 0C, I see a 010, offset 010, and then what else? I see a 0C, so let me actually annotate this in a different color. So I have a 010 right here, I have a 010. So 010. And then, oh, we have a 30, so that's a different, so this one's actually different. So now we have basically 3 variables that we have in this method. So we looked at this instruction. We start with the 0, we have a 0C right here. And these 2 variables get initialized to 0. Oh yeah, actually, and I missed this one as well. So I think that's it. So what we want to see here is, okay, let's see, anything else? Okay, I think that's it.
Hey, Andrew, can you answer a question?
Yeah?
Why are the add and the subtract, like in each function call, why are they not the same? Why are they different values?
You mean this thing? Oh,
Yeah,
these
why do you
subtract.
C but then add 10?
Okay, yeah, good question. So another thing we like to do with assembly, or like what people like to do when you write assembly code, is you want to align the arguments on the 16-byte alignment. So in this case, the printf only requires 1 argument. So we actually subtract 0xc, which is the 3 arguments, 3 32-bit arguments. So that way we are still on the same alignment. So we are in 16-byte alignments. And then when we add to ESP 10, that actually includes the push operation as well. So before we did subtract ESP by hex C, which is 12, and then we add another argument, which is 4 bytes. So that gives us 16 bytes that we push down. And then when we do the add, we actually push or pop 16 bytes back. So that's just something interesting. So going back, so here we see that first of all, we have a jump instruction. We go down here, and then we have this LEA instruction again. Can someone, so first of all, we have this LEA instruction right here and here. Can someone tell me why we might have an LEA instruction? Okay. Yeah. Does anyone know what the gets method is? Gets function. Okay. I heard one token. Gets a string. Okay. Close. So in C, we have a function called gets, and gets reads a line of text. A line, and it will actually take an array as input, a char array, which is a place to put your string. So here, we actually give a reference to somewhere on our stack, and that's our buffer or char array. So now we use that same thing over here, and then we see that some operation gets done over here. So we read something. We read this variable as hex 10, and we move that into EAX. We add this to this register here to our buffer array. So first of all, we want to notice something that's interesting. So in the for loop, what do we have? So in every for loop, what do we have in order to do the loop? And when do we know that we finished the loop? Does anyone want to give a guess?
You have the same conditions, break out the loop. And
Okay.
typically you have the declaration.
Okay, declaration. So what other way could you say the declaration is? Or like the variable? So, oh wait, you have something to say? Okay, yeah. So what I was trying to get at is, the idea is, in a for loop, we always have a counter. So something that keeps track of our which iteration of the loop we are in. So you usually see like for I equals 0, and then while I is less than some value, and then you increment the value of I. So here we actually see that same construct. So pretty sort of similar. So we first start with we have this variable, this one, the light blue one. We actually see that each time we go through this loop, this variable is actually incremented. So that is our index or our counter. And then we take the address of our buffer, and then we add our index to it. And that gets us the ith character inside that buffer, inside that array. And then the next instruction, we actually ask, what is the value of that byte in our array? And then we test it, and then we test whether if it's 0 or not. So I believe what this loop is doing is actually just looping through every single character and doing nothing else. So it's actually nothing much to this loop. It's just looping through every string, every character in the string until it reaches a null byte. So that's that. So now we see that there's also a hex C that is set to 0. We never see that it's actually set to any other value. So we actually see that this hex C is actually referenced again, and it's returned into EAX. So here we see that the function returns 0. So you can see that this really doesn't do much. It gets an input, and then it returns 0. Nothing much. So now, I think if you would like, there's some space to write, if you were to convert this into C code. I think we're a little bit short on time. So the exercise is, we also have a main method, which is also printed on your sheet. So over the week, if you have nothing else to do, feel free to look at the assembly code and follow the same steps that we did here, annotating it, and then see if you can figure out what it does. So yeah, I think today was a little bit more on the more material heavy, but I think part of it is this is kind of sort of how you look into assembly. It's honestly, to start off in assembly is there's a lot of detail, but as you look at it, it will actually become more clear. So if you like to, I think we have a few more moments. If you want to, feel free to look at the assembly right now. And if you have any questions, feel free to ask me or Sean. But if you have to leave, feel free to leave. I think we are done here.